Welcome everyone to episode 35, and we're going to do a really challenging question today. It's a question from a recent paper, and with the topics and the concepts involved, it relates to tissue demand and how it affects cardiac output. And the reason why I've got this picture here, it's like a landmine, or rather it's got many holes where you can actually go down, and conceptually you can spend hours just thinking about it and mulling over the different types of permutations in terms of where the cardiac function curves can actually turn out. So that's the reason why this is probably one of the most challenging question that I've done in recent times. And I think that at the end, I've got a sense in terms of how I actually want to approach the question. And I'm going to sort of give it a go, and yeah, we'll see how it sort of turns out. As always, the breakdown of the short answer question. So we're going to review the examiner's report, and it's very detailed. And there's a lot of good sort of interesting ideas which the examiner brings up, which I think is really important for us to have a read and also explore further as well. And then after that, I'm going to show you the literature that I use, present some key concepts, answer any questions that you might have, and I'll show you my answer structure, and then we'll all write an answer to time. Now, the question is from the 2020 question 8 paper, which is describe the process by which increased tissue demand for oxygen leads to an increase in cardiac output. Now, I thought another way to rephrase this question, which will be a little bit more interesting, is how does a decreased afterload increase cardiac output? And I think rephrasing that question this way sort of gave me a little bit of direction in terms of how I thought I should be approaching this question here. Going through the exams report, so let's go through it. There's quite a lot here to actually unpack. This question was poorly answered by the majority of candidates. It revealed widely held errors in understanding about core cardiovascular physiology. A passing answer should have contained the following points with explanation. And I've highlighted the green points that we'll need to include in our answer. So the green points are: increased oxygen consumption in tissues leads to local vasodilation. In other words, metabolic autoregulation. This reduction in local vascular resistance causes an increase in local flow for the same mean arterial pressure. In addition, there is a slight reduction in afterload, which increases stroke volume. Both of the above lead to an increase in flow from the arterial to venous side of the circulation. This increase in venous return then increases right atrial pressure and stroke volume via the Frank-Starling mechanism. I get the sense of how the examiner's thinking here. They're doing it very stepwise. And I think that looking through the concepts which I'll present, this is the way that I think we should also be thinking about the concepts, rather than an amalgamation of all the concepts that are there. Now, the next line is that the sympathetic nervous system is not directly involved in the above processes. And I can see why that a lot of candidates would have probably gone straight and talked about the sympathetic nervous system and its activation, especially in relation to exercise. That would be, I think, the most common answer, which the examiner is obviously not looking for. But that gives us an idea in terms of when we do answer this question, we do want to steer away from the idea that sympathetic nervous system contains the bulk of our answer. I think that we can include it, but it shouldn't be the bulk of our answer. And the next point that we need to include is that effectively cardiac output is controlled by the tissues. With exercise, sympathetic tone does increase, and this causes a rise in cardiac output, which is additional to the above. It should be noted that in the absence of increased preload, simply simply increasing heart rate does not reliably lead to increased cardiac output. That's a really interesting concept there. And I think that it goes against what we sort of define cardiac output as, which is cardiac output equals heart rate times stroke volume. And I can see where a lot of candidates would be talking about that idea in terms of increasing sympathetic nervous stimulation, increasing heart rate, and therefore increasing cardiac output. But I'll show you a diagram from Guyton, which I think this examiner is alluding to, where that idea that just simply increasing heart rate without actually increasing preload doesn't actually increase your cardiac output. So that's, I think, something that we should just put a circle around. Now, this is what we should not be including in our answer. So these were the following common errors. Local vasodilatation causes hypotension, which is sensed by baroreceptors and causes increased sympathetic tone, which increases cardiac output. This is incorrect. Hypotension is not required as an initial step in order for cardiac output to increase. During exercise, the blood pressure increases. Second point, increased oxygen consumption, metabolism leads to a fall in PaO2, a rise in PaCO2, fall in arterial pH, which then activates the sympathetic nervous system via the chemoreceptors. This is incorrect. Even during strenuous exercise, people do not normally become hypoxemic or hypercarbic. It has been postulated that there are chemoreceptors within tissue beds, especially muscle, but these have never been identified. And that line here is from Pappano. Another incorrect statement, the heart is a demand pump, which means that it will pump enough blood to match tissue demand. This is oversimplified. Now, this is, I think, what the examiner wants us to put in the answer. When we refer to the heart as a demand pump, this means that the forward cardiac output is matched to the venous return. Several high-scoring answers were able to use Guyton curves to add more detail to their answer. However, the majority of candidates who attempted to incorporate Guyton curves only became more confused. This is really, really important. I think that a lot of times we're going to be drawing Guyton curves here. And I think that when we do so, we do want to draw it sequentially so that there's some logical flow to that idea. And we don't want to just draw cardiac function and vascular function curves without actually having sort of an explanation or a step towards what the answer is. Now, this material is well covered in the Essential Core textbook, Pappano and Weir, Cardiovascular Physiology, 11th edition, especially chapters 9, 10, and 13. For those interested, Guyton's original article is well worth reading. Guyton, a regulation of cardiac output. And that's the one that I've attached as well in the latest post. This is a summary of the examiner's report. And the main points are that an increase in venous return from two things, from metabolic autoregulation via increasing oxygen consumption leads to local vasodilation, which then increases local flow for the same mean arterial pressure. And we're going to explore that idea further on. The second point is that a reduction in afterload increases stroke volume. And again, we're going to explore that concept. The other main point is that an increase in the venous return results in an increase in right atrial pressure, as well as an increase in stroke volume via the Frank-Starling mechanism. And then the third thing is that we need to draw Guyton curves to illustrate these points. And you can see the difficulty or the challenge here is that when we do draw those Guyton curves, we want to be able to tie it into these concepts here. And I think that that's where the challenge of the answer lies. This is the literature that I've used. So I've used that Guyton article. I've used the chapters which the examiner has suggested. And I've also used chapter 30 in Power and Chem. And the reason why I've done that is that they do bring up another idea or another way to sort of present that information, which I really like. And I'm actually going to use that to my advantage when I create my answer later on. This is the summary of the Guyton article. So the one that I've attached, it's quite detailed, but I've just summarized a couple of the key points here and also going through some of the diagrams. Now, there are 3 factors in cardiac output regulation. 1, heart function, 2, peripheral resistance, and 3, filling. Later on, Pappano will describe it as both heart and also blood vessels. And we will explore that idea in terms of how Pappano actually presents that information. But the way that Guyton presents it, it's those 3 things: heart function, peripheral resistance, and filling. Guyton goes on to say that the heart permits the cardiac output to be regulated from 0 to max. So it's a permissive function, and it's based on the Frank-Starling mechanism. And the idea is that even if you have a denervated heart, it should still be able to perform as described in this diagram here. So this is the normal heart here, the one up here. So it goes from 0 to about a max of 13 liters per minute. And what the heart does is that it functions around 5, but it permits the heart to change the cardiac output along this line. So it's a permissive function. And that's a concept that Guyton was trying to describe. Now, I don't think that we need to sort of hold too strongly onto this idea, because, you know, Pappano does sort of think about it differently, but I think it is interesting in terms of the way that sort of Guyton sort of thinks about the way that the heart functions and the way that it is really a permissive organ, and that really cardiac output is controlled by the peripheries. And this was really, really interesting. I really like this concept here. So the concept is that peripheral resistance is the primary regulator of cardiac output, but that the sum of all tissue organ blood flows equals cardiac output. And this concept here I thought was really, really insightful, because it makes sense. Because when you think about individual organs, hypothetically, let's say for whatever reason, you're increasing, let's say, blood flow to the brain through all those other factors which are involved with the regulation of, cerebral blood flow. But let's say everything else in terms of the other organs, their tissue blood flow remains the same. Now, if you think about it mathematically, because you've actually increased blood flow to the brain, that should also theoretically increase your cardiac output. And so this brings up the idea that cardiac output is really the sum of all tissue and organ blood flow. And I think that was really, really insightful. I know sometimes we can sort of build on that concept and think about, moving blood from one organ to another, or one viscera to another. And certainly it happens with exercise. But I think if everything remains the same and you were to increase blood flow in one tissue or one organ, then really your cardiac output should actually increase as a whole. And this was a really interesting experiment. So what happened here was that they had a circuit and they had an AV fistula. And what they did was, at this point, they actually opened up the AV fistula and allowed quite a significant amount of flow to go through the AV fistula. And as you see, as they open up the fistula, the resistance, which is here, the pressure, which is a reflection of the resistance, dropped. But what was really interesting was that the amount of flow through the AV fistula was almost the same as the amount that the cardiac output increased by. In other words, the AV fistula allowed that flow to bypass and head back to the heart. And the amount of flow going through the AV fistula was the same as the amount that the cardiac output rose by. And I thought that was a really, really interesting experiment. Now, this is a diagram in this article which shows that two concepts. So they've got the idea that what's important here is the pressure in the bag. And then the second thing is the resistance from the bag to the pump. Now, the concept here is that flow of blood heads into the systemic circulation, and that builds up the pressure inside this bag here. And it is the pressure in this bag, right, in this bag here, which then pushes the blood back through the veins and back into the pump. And what happens is that if this pump tries, so if the heart, this is analogous for the heart, if this heart tries to pump more blood, okay, this way, and there's inadequate flow coming back here, what happens is that these tubes will collapse, okay? And because these tubes will collapse, that actually prevents further output. And this brings light into the concept which the examiner is talking about in terms of, even if you increase your heart rate, so if you increase the amount of cycles that this heart is pumping, if you actually don't have blood coming back, it's actually not going to increase your cardiac output. And that's a really interesting concept to think about. Now, this one here. So this concept is talking about the idea of venous versus arterial resistance. And Guyton here says that venous resistance is more important than arterial resistance. So venous resistance plays a much more important role than arterial resistance when it comes to cardiac output. And the reason for that is that anything that increases venous resistance will cause a backlog, okay, of blood into these veins, which are distensible. Whereas anything that increases arterial resistance, these systemic arteries, they don't actually hold that much blood. And so because of that, what that means is that anything that affects venous resistance is going to be affecting things like the amount of circulating blood volume. Whereas things that affect arterial resistance tends to just affect pressure, but has less to do with sort of the circulating blood volume. And Guyton goes on to say that's the reason why hypertension is not always associated with a decreased cardiac output, just for this very reason here. So you've got an increase in arterial resistance, but because the blood doesn't sort of back up into the systemic arteries, there's still forward flow, okay? But the result of that is that you get increase in your pressures. So that was really interesting. Now, this next diagram here, this one here is about the idea of blood volume and its relation to circulatory capacity. And that is expressed as the mean systemic filling pressure. Pappano calls it the mean circulatory pressure. But I think most texts will call it the mean systemic filling pressure. And the things that affect it are transfusion, so the amount of blood volume, as well as the sympathetic effect on the circulatory capacity. And what they mean is that this is normal. And if you have sympathetic nervous system activation, what that does is that effectively increases the tone or decreases the capacity. And so that blood that comes in, there's actually more pressure in here to actually drive it forward. And that's quite an interesting idea in terms of how the sympathetic nervous system actually works. And also the idea of how mean systemic filling pressure is affected by things like blood volume, as well as your sympathetics as well. And we're actually going to build on that idea when we look at some graphs in Pappano. So look, those were the main sort of diagrams I wanted to go through in Guyton. And it is from the 1960s. So I think Pappano presents a much more modern version, all right, in terms of the ideas of cardiac output. But certainly I think the ideas that Guyton presented is a really sort of interesting concept that we can sort of build on. Now, we're starting from chapter 9, which is the peripheral circulation and its control. I've really just focused on vasodilation, which is via intrinsic and extrinsic. The other sort of terms you'll hear about are neural versus humeral or central versus local. And vasodilation, when we talk about intrinsic, is due to low dose adrenaline via beta 1. Now, vasoconstriction is a major part, and vasoconstriction will occur via noradrenaline on alpha 1, angiotensin 2, endothelin, vasopressin. But for this question, I'm just going to focus on vasodilation, and that's really just with low dose adrenaline. Okay, but you can see that extrinsic actually plays a much bigger role. So the extrinsic factors, so there's myogenic autoregulation, but the one that we really want to focus on is flow metabolism coupling. And that produces metabolites such as lactic acid, CO2, hydrogen ions, potassium, adenosine. And also, I think they also talk about low partial pressures of O2 as well, being a factor in terms of flow metabolism coupling. Pappano goes on to talk about the idea of capacitance versus resistance vessels. And what are these exactly? So capacitance vessels are often the veins, and I've just left the page there to sort of let you know where it's from. So that's on page 139, where he describes capacitance vessels as veins and arterioles as resistance vessels. And that's really important to acknowledge, because when we talk about vasoconstriction versus venoconstriction, so vaso is for the arterioles and veno is for the veins. It really sort of leads us and helps us understand how it affects the vascular function curves. So with capacitance vessels and veins, it's more responsive to sympathetic nervous stimulation, and it mobilizes blood from tissue to the circulating blood volume, and it increases your mean systemic filling pressure. It is less responsive to vasodilator metabolites. With the resistance or arterioles, sympathetic nervous system stimulation reduces blood flow and increases arterial pressure, and it does not change your mean systemic filling pressure. So there's no change in that. And we'll show that in the vascular function curves and how resistance changes it or rotates it. I really, really like this diagram. And this will be something that I think that I'll use in my answer. And this is the idea in terms of what affects cardiac output. So remember that Guyton said that the factors that affect cardiac output were cardiac function, resistance, and blood volume. But the way that Pappano presents it, they've got two factors. So they've got cardiac factors, and then they've got coupling factors. Cardiac factors are the heart rate and myocardial contractility. Coupling factors are determined by both the heart and the blood vessels. And these are preload and afterload. And I really, really like the way that this is presented. In other words, that if I got asked a question on what are the factors that affect cardiac output, I would say there are cardiac factors and coupling factors. Cardiac factors are heart rate and myocardial contractility. Coupling factors are preload and afterload. And I think that really sums it up really well. Now with the cardiac function curves, so this is based on the Frank-Starling relationship. And it describes the dependence of cardiac output on preload. What do I mean by that? It means that your cardiac output is your dependent variable. So it's going to be on the y-axis, and preload is your independent variable, and it's going to be on the x-axis. You'll see different iterations of how this graph is drawn, and I've just written them in parentheses here. So it can be described as your left ventricular end diastolic pressure, CVP, or right atrial pressure, and you'll see different variations of that, okay? But it literally stands for preload. And the cardiac function curves are characteristics of the heart itself. And it is affected both by cardiac factors as well as coupling factors as well. In other words, that when you look at the graph, you will see that the things that change it are both cardiac factors, so that's heart rate and contractility, and also coupling factors. So the coupling factors are afterload and preload on the x-axis. So coupling factors are preload and afterload, and then your cardiac factors are heart rate and contractility. And you can see that the cardiac function curves are affected by all that. This is very, very different from the vascular function curves. And this is where it gets really confusing because of the way Pappano presents vascular function curves. Very different to how other textbooks present it, okay? And the reason for that is that Pappano says that vascular function curves describes the dependence of preload on cardiac output. Remember before, so I'll just quickly show you, when we talk about cardiac function curves, it was describing the dependence of cardiac output on preload. This is the opposite. It's now describing the dependence of preload on cardiac output. So that means that your dependent variable, preload, is on the y-axis, and your independent variable, cardiac output, is on the x-axis. And this is characteristic of the vascular system, independent of the heart. It's affected by your peripheral resistance, your arterial and venous compliance, and the ratio that they give is that your arterial compliance is 1/20th that of your venous compliance. So the ratio is 1:19. And then the third thing that affects it is blood volume. And look at the way that they've drawn the vascular function curve. So I think most of us would be looking at this going, what is this? Normally we have cardiac output on the y-axis and CVP or preload on the x-axis, but this is drawn the other way around, because what Pappano wants to show is that now that cardiac output is the independent variable and CVP is your dependent variable. And so what happens is that, as you increase your cardiac output, what you're doing is that you're actually translocating blood volume from the venous side to the arterial side, as in you're basically drawing blood away from the venous side, which is why that as you increase cardiac output, your CVP starts to drop. That's a really interesting concept. And I think that sort of hopefully helps to also explain the ideas that it is an interdependent system. And so what happens is that at maximal cardiac outputs, what happens is that drawing of the blood becomes extreme, so much so that the pressure on the venous sides starts dropping to less than 0. And when that intravascular pressure is below the extravascular pressure, you get that collapse. And that's why that limits the maximum amount of cardiac output that can be delivered. And so I hope that concept makes sense to you. This idea that as you increase cardiac output, so as you increase the pump on that drives blood on the left-hand side, it's actually sucking blood from the right-hand side. And as it sucks more blood, this is why the pressure drops. But it drops to a point where at this point here, that's when it starts plateauing. And you see that this graph drawn obviously the opposite, and I'll show you how it's drawn in Power and Chem. And I think that's probably the most common way that we're gonna, most of us are gonna represent that graph. Okay, and for me, I would probably draw it the other way. I wouldn't draw it this way. I think that this way just helps with my understanding, but I would be more comfortable drawing it the other way. All right. This is the another sort of interesting figure, and it just talks about the interdependence between the arterial and venous side. And as you can see, that cardiac output here starts tailing off. And as your cardiac output starts dropping, your arterial pressure drops. But look what happens to your venous side. It starts increasing. So that you can see that there is that interdependence or that inverse relationship between the two. And eventually at cardiac standstill, they meet at the mean systemic filling pressure. Okay, and that's where they end up. This is a continuation of that idea. So what we have here again is the idea that the pressure in the venous side is inversely related to the pressure in the arterial side, which is affected by your arterial tone. And that's taken into account that everything else remains constant. So the assumption here is that your total peripheral resistance is 20 millimeters of mercury per liters per minute. And this is at a cardiac output of 0. So at cardiac output of 0, that's at your mean systemic filling pressure of 7. And at cardiac output of 1, you can see that the arterial pressure increases to 26 and your venous pressure drops to 6. And that at a cardiac output of 5, which is normal, your arterial pressure increases to 102 millimeters of mercury and your venous side drops to 2. So you can see that there's an inverse relationship. And the reason why the changes are what they are is because of the compliance of each side. So remember that the venous side, it's much more compliant. It's 20 times more compliant than the arterial side. So that for a given change in volume, because the venous side is more compliant, there's going to be less change in pressure, and vice versa on the arterial side. Okay, it's less compliant, which means that for a given change in volume, there's going to be a larger change in pressure. Then we move on to the different iterations of how these graphs can be drawn. And you can see here that increasing transfusion will move the curve to the right, and anything that decreases blood volume, such as hemorrhage, will move the curve to the left. And you can see how that with transfusion, it moves your mean systemic filling pressure. So your mean systemic filling pressure is the one here. Okay, so it starts from 7. With transfusion, it goes up to about 9, and then with hemorrhage, it drops down. This is how resistance affects the vascular function curves. So you can see that because the arterioles have only a blood volume of 3%, I think Pappano's quoted, it doesn't actually contribute to your mean systemic filling pressure. And so anything that increases your arterial tone will just cause a rotation from your mean systemic filling pressure. So if there's a vasodilation, it will rotate it up. And if there's vasoconstriction, it will rotate it down. Now, just to summarize, the central venous pressure or the preload depends on cardiac output, which is affected by your blood volume, your venomotor tone, which is from venoconstriction, and also the blood reservoir, where it's venoconstriction of vascular beds, such as skin, liver, lungs, and spleen. And the first 3 points, so blood volume, venomotor tone, and also venoconstriction of blood reservoirs, which move blood into your circulating volume, they are factors that affect your mean systemic filling pressure. The fourth thing, peripheral resistance, which is due to your arterial tone, that is not affected, as in your mean systemic filling pressure is not affected. Okay, and the reason for that is that it's quoted that the arterioles only represent 3% of the blood volume. Now, I've got a little exercise here, and what I'm going to sort of show you are those concepts here. So you can see that the way that Pappano now has drawn them is, I think, that the way that we're very sort of more familiar with how they're drawn, with in terms of the CVPs on the x-axis and the cardiac output on the y-axis. And I just want to sort of start off with the idea of blood volume. So blood volume, so now your mean systemic filling pressure is here. So what's going to move it off to the right, okay, or shift it to the left are things like blood volume, your venomotor tone, and blood reservoir, okay, blood reservoir. And these two are from venoconstriction. Now, when we talk about peripheral resistance, that's primarily due to your arterial tone, and that's going to rotate it. So it's going to rotate it up if there's a reduction in resistance, and then it's going to rotate down if there is an increase in resistance. And those are the different permutations of this graph here. Now I'm going to move on to chapter 13. There isn't sort of too much here. It has to do with exercise. And I've just sort of given a summary that the cardiovascular changes in exercise are due to, again, neural activation and local changes. And we've gone through the local changes, and I just want to summarize the neural changes. So that's activation of your sympathetic nervous system. And Pappano actually describes it really nicely, and I quite like the way that they've set this out, so that the activation of your sympathetic nervous system occurs through 1, central command or cortical activation, 2, reflexes in the contracting muscle, which can be either mechanoreceptors or chemoreceptors, and this is the one that the examiners were alluding to. So remember that these receptors actually head back and activate the vasomotor center. So these are not local receptors, okay? And then thirdly, baroreceptors are involved with exercise. As you can see, baroreceptors are involved, you know, in exercise. So I think the examiner probably didn't want you to talk too much about the baroreceptors, and I think that's something to be aware of, that even though, yes, it is involved with sympathetic nervous system activation during exercise, don't spend too much time talking about it. And then the second bit is local, and we've talked a lot about sort of the flow-metabolism coupling involved. This is the graph which shows you the changes in exercise. And I like this one. So I'm going to try and include this in my answer here. So, you know, this is normal. And then these are the changes in exercise. And I think what's really interesting here is, so you can look at the ideas sort of sequentially. So, you know, there is an increase in your mean systemic filling pressure, so shift to the right. So that's from, remember, venoconstriction causing an increase in your venomotor tone, as well as increasing your what I call sort of sequestration of blood from your viscera back into your circulating volume. So this is from blood reservoir. Sequestration. The other interesting thing is that you can see it's rotated up. Okay, so the angle's rotated up, and that is because of a decrease in resistance. And that's to do with the vascular function curve. Now you look at the cardiac function curve. So the cardiac function curve has increased, and that's due to a number of things. So that's due to increase in contractility. There is also a decrease in your afterload. And there is also an increase in your heart rate as well. Now, this diagram here just shows you how blood flow changes during exercise. So as cardiac output and blood flows to active, active muscles, what happens is that visceral blood flow, so things like the splanchnic circulation or the renal circulation, decreases. And then you also have, blood flow initially increasing to the skin. Here, that's to do with heat loss. But as you increase the intensity, you can see that skin blood flow actually starts decreasing and starts constricting, okay, as you sort of reach your VO2 max. And the heart and the brain, that remains fairly sort of constant and doesn't actually change much with exercise. So the important components here is that your visceral blood flow, which represents your blood reservoir, actually starts decreasing, and that blood actually starts moving away to other areas such as muscle. Okay. Now I've done this slide here just to compare some concepts and some terms, because I think that's really important. And I think that's half the challenge about this exam, is understanding the different terms that are being used and what they mean. And, Guyton, when he talks about arterial resistance here, Pappano, I think what Pappano is referring to with that is things like arterial tone or vasoconstriction. And then when Guyton talks about systemic veins, so this reservoir here, I think Pappano is referring to things like venomotor tone or venoconstriction. And then lastly, when Guyton talks about venous resistance, which is this tube here to the pump, that has to do with things like venous collapse, or when your extravascular pressure is actually more than your intravascular pressure. In fact, venous resistance is probably not talked about, but it does play an important role, especially with the ideas of intermittent positive pressure ventilation, okay, or even with laparoscopic surgery and pneumoperitoneum, and the idea in terms of how a pneumoperitoneum can actually restrict the amount of venous return. And that has to do with the idea of venous resistance. So some interesting sort of ideas here. Now, finally, I want to go through a couple of diagrams from Power and Cam, because I think that will give us an idea in terms of what is commonly presented with the cardiac function, or with the cardiac function as well as the vascular function curve. So this is chapter 30, venous return and vascular function. This is pretty standard, I think, this curve. So this is the cardiac function curve, and you can see instead of having CVP on the x-axis, you've got right atrial pressure. And again, with sympathetic stimulation, you get it shifted up, and then with a reduction in sympathetic stimulation, you get it shifted down. This is really interesting. So this is why I think it's nice to sort of use this graph here, is because of this. Look at how Power and Cam has labeled the y-axis here. He's labeled it as venous return instead of cardiac output. So Pappano labels it as cardiac output, but Power and Cam has got it as venous return. So this is for the vascular function curve. And the reason why I think that's important is that I think it allows us, when we think about the steps sequentially of how local vasodilation increases venous return, we can use this graph to actually explain that. Because what we can say is that with a reduction in your resistance through vasodilation, you get that rotation up. And as you can see that for a given right atrial pressure, you actually increase your venous return. And this was the idea that the examiner was talking about in their exam report. And I think by using this graph here and using the idea of venous return on the y-axis, we can actually incorporate that that point into our answer. And again, this graph here just describes what I just sort of drew before. So that's that idea of having venous return on the y-axis. And finally, we've got this graph here, which is a combination of cardiac output or venous return. So I think that's another way that I think that, you know, if we do draw this diagram, and I've sort of visualized it in my head how I'm going to be answering this question, and I think that you know, you can either draw the graph separately, or you can draw the cardiac function and the vascular function curves together. And I suspect that you know, what I'll do is I'll draw them together, but I'll label it as cardiac output or venous return, and then I'll have a couple of points in terms of the movement from, you know, A to B to C. I think that's what I'll do. Okay. And finally, this last graph. So this last graph is interesting because it contrasts to what Pappano drew. And this one here is for sympathetic activity. And so this is not for exercise. And I think that's why there's a little bit of a difference. And I think you can probably spot the difference already. The main difference is that resistance is actually increased, so that if you look, the angle is actually lower, okay? Whereas remember, in the other one that we drew, so from Pappano, resistance was actually decreased and there was actually a tilt up. So this one's a little bit different in the way that Power and Cam has presented it. And the way that I think we can reconcile this is that this is just for an increase in sympathetic activity and not for exercise. And that's why he has it rotated down instead of having it rotated up. This is my answer structure here. And what I'm going to have is I'm going to have a definition of cardiac output and a definition of flow metabolism coupling. And that's going to lead on to the idea of a reduction in systemic vascular resistance or afterload. And then I'm going to incorporate how that affects the vascular function curve. And then after that, how that affects the cardiac function curve. And thirdly, I'm going to make a quick note just about exercise and its effect on the effect of the sympathetic nervous system. So that's probably the way that I'm going to frame my answer here. All right. So let's go. So I'm going to have my definition. And then after that, I'm going to have how afterload affects my vascular function curve, and also the cardiac function curve. And on my last page, I will talk about exercise. So cardiac output, CO equals MET minus CVP by resistance and cardiac output is affected by heart rate and contractility, and these are cardiac factors, and then preload and afterload, and these are coupling factors. And I think that can bring on to the idea of afterload, because what I'll say is that increase in oxygen consumption in tissues is increase in tissue blood flow for a given map via Flow-Metabolism Coupling, which is essentially just local vasodilation to release mediators such as lactic acid, CO2, H+, K+, adenosine. And then this results in increased cardiac output, as one cardiac output equals sum of all tissue blood flow, two, decrease SVR and afterload, increases venous return as per the vascular function curve, rotation clockwise from the systemic filling pressure. And you know what? I'm actually going to draw this on a separate page here. So I'll have this diagram. CVP, cardiac output at this point is mercury 0, 7. Increase in venous return leads to increase in right atrial pressure, preload, and increases volume by the Frank-Starling mechanism. What I'll do is control this one here. So what I'm going to do is this is A to B, CVP, CVP, right atrial pressure, preload, point A to point B. Then I do want to draw another one next to here. Point B. Okay, so point A to point B. So that would be point A to point B. Okay, and then 3 decreasing SVR after load increases cardiac output as per the cardiac function curve. Translocates blood from the venous to arterial side, returning right atrial pressure preload back to its original point, but further increasing cardiac output. In other words, point B to point C. Right, so my last bit on exercise. Increasing O2 demand due to exercise will also activate the sympathetic nervous system. SNS increases cardiac output via 1, increasing your mean systemic filling pressure via venoconstriction that increases the motor tone and sequestration of blood from visceral beds, and 2, increases contractility and heart rate. All right, last minute. CVP output per minute. Or let's return. So we've got exercise. Shift to the right, and then translocate it up. Up, right, and upwards. Rotate it. A to B, A to B. All right, it's done. It's 10 minutes. So I've done 4 pages, and I'll just sort of show you what I've done. Got my definition, which I've just done it as 1 page, just sort of half page actually. And then what I've done is I've just talked about the idea of how afterload affects the vascular function curve and cardiac function curve. And then I've sort of related it to this diagram here, where point A moves to point B, goes to point C. And then after that, just the idea of exercise. And as you can see, this was just a last minute thing, so I haven't had time to sort of put any numbers in, but sort of get the idea. Tough question, very, very tough question. And yeah, I think that, I guess with a bit more thought, I would probably write this a little bit quicker and hopefully have a bit of time to sort of make this graph look a bit nicer. And looking at this, I probably shouldn't have drawn this arrow from A to B. I should have just left it, because I think drawing this arrow from A to B really sort of confuses this picture now that I'm looking at it. So it's always good to sort of try it just to see how it sort of presents itself. And I think next time, I'll probably leave it like this, just A, B, C. I think that's a lot easier to follow.